Welcome back to the Moldex3D Advanced Tips and Tricks. My name is Alex Baker, and we're going to be going over result interpretation for the filling and packing stages, the first of two result interpretation sections. In this section, we're going to go over the 9 questions that you need to ask yourself for a level 2 or a filling and packing analysis. We're going to interpret the results using some advanced interpretive tools. And then we're going to make informed decisions based on the simulation results.
All right, so when it comes to the filling analysis interpretation, we usually follow what's called the Flowpack Analysis Guide, or what we more commonly call the General Moldex3D Workflow, or GMW. This basically just lays out the process for going through the result interpretation in a systematic manner. So we're going to assume that we've already gone through all the pre-processing steps, which are on the left side of this flowchart. On the right side here, we have 9 different questions that we'll typically ask ourselves to evaluate the flow and to qualify whether we have a good flow, quote unquote, or maybe if there's any improvements or optimizations that need to be made. All right, so we're going to go through each of these 9 questions systematically, and these are the 9 questions that you should always answer, or at least discuss or analyze when you're looking at the results of a simulation. But I always recommend to go through the flow and pack analysis and the cooling analysis before looking at your warpage results. If you look at your warpage results first, you're going to be biased and you're going to be trying to figure out why a certain phenomenon occurred. It's always better to get an idea of what you're looking for, or you should get an idea of what you should be seeing in the warpage before looking at the warpage. It'll help you out a lot, and it'll answer more questions than just looking at the warpage results alone. All right, so the first question here is, will the part fill? If the part isn't filled completely, obviously you're getting a short shot, and we want to prevent that. So that's why this is the first question. If your part isn't filled, then you're likely going to have to run another simulation anyways, because probably 99.9% of the time a short shot is not desired. All right, so the first thing that we're going to do, I'm going to kind of bounce back and forth between this presentation and the result panel. So I'm going to go over to Studio. When your project opens, it'll probably have the mesh overlaid. We're going to turn off the mesh here. Usually for result interpretation, the mesh gets in the way more than it helps. So what I'm going to do is I'm going to go towards the top here. There's a little toolbar right at the top middle of our screen. I'm going to go right in the middle of that toolbar, which is the 5th button over. It looks like an orthographic cube. I'm going to click on the drop down and go to the 3rd option, which is show feature lines with shaded faces. All right, and it'll essentially just get rid of our mesh lines while still showing all of our feature lines. All right, so there's 4 primary results that we're going to look at here. The first one is the melt front time. Then we're going to get into sprue pressure, flow rate, and finally, the ultimate test is the filling log file. So the first thing we're going to do is get into the melt front time. So to access the melt front time, we're going to go to the filling results. So you can go over to the left side of your screen, go to filling, and we're going to get right into the melt front time result, which is the first result that should show up. All right, so as far as this question is concerned, will the part fill? It's very visually indicative with this result, because you'll actually see that the part will not be completely filled. There are instances where you get to like 99% filled, and we'll handle that scenario in just a few moments. But for the most part, if you get a short shot, it'll be pretty obvious. And in the blue region of this color contour, you'll be able to see that there's some sort of unfilled region. It'll look something like this. I'm just taking my animation back slightly. It'll look something like this, where a portion of your geometry just won't be colored. All right, in this case, we can see that the part is, in fact, 100% filled visually, but that's not always the end of the story, because there are, like I mentioned, there are instances where you get very, very close to a full shot, but not necessarily all the way to 100% fill. So the next result that we usually look at, actually a pair of results that we usually look at, are in the XY curve section. And this is going to be very important. I'm actually going to switch to metric units. If you aren't in metric units, if you're looking at this sprue pressure result, when you go into the XY curve, the first graph that shows up is the sprue pressure. That's the first curve that we're going to look at. And it'll make sense in just a moment why we want it to be in metric. But if you're not in metric, you can go up to the preferences menu at the top left corner of your screen. And then you can go to units. And you can change the simulation units. Make sure you don't change the design units. That's not going to help here because we're in the simulation analysis stage. We want to change the simulation units, and I recommend to either change to metric or SI, both of them, or change to metric, either the CGS or SI options. And the reason for that is because we're going to overlay another curve on top of this. So to overlay the second curve, which is going to be our flow rate, I'm going to go over to my history button. So if you go into the result tab and then you go to history, we can see that I already have sprue pressure in my plot contents. Now I'm just going to take my flow rate and move it over to the right. And that will allow me to kind of overlay both of these graphs at the same time. You can just close out of that window if you want to. All right, so what we have here, and the reason that we switched to metric is because we only have one y-axis here. If we showed in PSI, the value would be very skewed for the, or we would be able to see the sprue pressure plot very obviously, but the flow rate plot would be pretty much at zero, or it would look like it's at zero, but it's actually just because the values would be very different. So now that we have both of these graphs overlaid with one another, we can see that in the filling stage, for this case, we can see that we have pretty much a constant flow rate over the entire process. And then at the end, when we have our switch over to our packing stage, our flow rate starts to drop down. And the reason that we have a constant flow rate is because during the filling stage, we're using velocity controlled fill. So we're actually specifying our flow rate and we're using that flow rate as a constant value. And then based on the resistance of filling, our pressure will continually increase here. So this is what a normal graph set should look like. Let's take a look at what an abnormal graph set would look like. All right, so this is one scenario where you would get a short shot in the filling stage. So you can see that the pressure, this is the sprue pressure plot, the sprue pressure kind of gradually increases, and then eventually it actually hits a maximum value. This is what we call the pressure limit or the pressure ceiling in the simulation. And you can see that actually the flow rate graph, when the sprue pressure becomes constant, or when the sprue pressure is no longer changing, we can see that the flow rate changes. And that's because the sprue pressure and the flow rate are kind of dependent on one another. Whenever the flow rate is constant, the sprue pressure will change. Whenever the sprue pressure is constant, the flow rate will change. That's the way that you should always see it. So what actually happens here is when we reach a maximum value, we're actually switching over to our packing stage. We're switching over to a pressure-controlled flow at this moment, and that's why our flow rate changes. We can actually see that in our results right here. We switch over at this point, which is actually the intended switchover point, and then at that point, that's when we see the flow rate start to decrease. Now, this is a normal short shot scenario. Usually, if you try to fill your part too much with pressure-controlled fill, the amount of resistance for flow is going to overbalance the ability of the material to flow, or the force that we're actually applying. So it will eventually cool off in short shot in that scenario. Over here, we have a more extreme short shot where we've set the pressure limit a little bit lower. And you can see that the pressure limit gets hit almost immediately. And because of that, we can see the flow rate drops dramatically right at that moment. So this is something that you should be looking for. At least you should be looking at the sprue pressure plot for a short shot scenario to see if your flow rate graph starts to change before you intend. All right, and then the last and probably most probably the best way to figure out if you have a short shot, the most obvious way to figure out if you have a short shot is through the filling log file. So I'm going to go up to my log up here in my result panel. I'm going to go almost all the way over to the right to the log. All right, and I'm going to scroll down. You can see that at the top here we have a lot of our inputs to the simulation. And then below the inputs are going to be all of our pretty much just the computation table. Now there's 6 items in this table. I'm not going to go through all 6 of them because they're pretty straightforward, honestly. The most important one that we want to look at is the 5th one, which is our fill percentage. So the fill percentage is actually the amount of our cold runner plus our part that has been filled. And ultimately, if we get a full shot, then this value will eventually reach 100%. So I'm going to scroll all the way down to the bottom of this table, and hopefully this fill percentage gets all the way to 100, which in this case it does. Now this table, you can actually see that it gets very, very specific. There's 3 decimal places that it goes to. So if you were to get a 99.9% short shot, which has happened, then this log file will be the best place to find that out. Sometimes it's very difficult to find that visually through the melt front time result, but through the log file, you're always able to figure out if you have a short shot or not. So at the end of the day, this is the best way to figure out if you have a short shot. It's just go to the log file, go to the bottom of your computation table here and see if you have 100%. If this value does not reach 100%, then the filling log file will display a warning message, or actually I think it'll be an error message, and it'll tell you why you short shotted, whether you became pressure limited or whether your material just froze off, your melt temperature was a little bit cooler than it should be. There's a various amount of reasons why you would get a short shot, but the log file will be your best way to diagnose why that short shot occurred, if it did. All right, so I'm going to close out of the log file, and we'll move on to the second question, which is going to be, is the flow balanced? So that we know we have a full shot. Now we can start to evaluate what our flow actually looks like. And there's 4 results. Really, most of the time, it's just going to be 3 results based on our modeling. Based on our modeling setup, the gate contribution might not be necessary. But melt front time is going to be pretty much the most crucial, paired with the flow rate and the sprue pressure. These are going to be the 3 results that we're going to look at primarily. All right. So looking at our results here, the first thing I'm going to go to is the melt front time. If you still have the graphs overlaid like this, then you can simply just go up to the top right corner of the graph, and you can see this little red X here. You can close out of the graph that way. All right, but we're just going to look at the melt front time result, which should still be overlaid because that's what we were looking at before. And instead of just looking at the 100% fill, I'm actually going to play the animation of my filling. So I'm just going to press the play button over in the animation section of the result panel, and we'll see the flow gradually fill out our part, which is cool and all. But what we're more interested in, and this is where flow balance gets its name, is we want to evaluate how the material, or at what time the material is getting to each of our end of filling locations. So what I'm going to do, I'm actually going to stop my animation here, and I'm going to go to what I call the VP switch point. And you can figure out where your VP switch point is. If you go back to the Home tab, you can open up your process. If you go over to your filling and packing settings in the process wizard, you can figure out what your VP switchover is. So for this case, I have 98% as my VP switchover. And for that reason, I'm going to go back to my result tab in the animation percent input here. This is actually a percentage of our flow. I'm going to go to 98%. And at my VP switchover, I should see that all of my end of fill regions, all of my expected end of fill regions are unfilled. So we can see that in this case over here, our flow is not yet completed at 98%. And then I have one other on this side. You can see that this side is also not filled at 98%. This is the ideal scenario, and the reason why we want to make sure that we have a flow balance, actually there's 2 reasons for it. First of all, If we balance our flow, then we are going to optimize our flow length, which means that we're going to optimize the amount of pressure required to fill the part. If I were to place my gate over here on my part, maybe closer to this end of fill down at the bottom right corner of my part, then my flow length over to the other end of fill is going to be much longer, and the resistance to flow along that flow length is going to be much greater. So my pressure required to fill my part is going to be higher, which might actually push this part into a higher press, which would increase production costs and so on. So making sure that your flow length is optimized will optimize your pressure distribution throughout your part, and ultimately get you a it'll make your production costs a little bit lower potentially. The other reason that we look at the other reason that we look at flow balance is to eliminate any unnecessary spikes. So when I say unnecessary spikes, I'm talking about pressure. So usually if you have an unbalanced filling scenario, if your end of fill regions are not if one end of fill region is filled out and the other is not, then you'll actually get a pressure transmission through the gate, and that will cause a pressure spike, which we'll be able to very easily see through a result called the sprue pressure. So I'm going to go again back down to the bottom here, XY curve sprue pressure, and we're not just going to look at whether or not our pressure goes to a constant value. We're actually going to look at the contour of this sprue pressure plot a little bit more closely. So we can see that in general, the pressure kind of increases quickly through the gate, which is pretty expected, and then it goes gradually. And actually, there's a small spike in the middle here, which we'll definitely want to be taking a look at that. Any abnormalities that you see in your sprue pressure plot should be investigated. And we increase until we get to the peak value here, which is our switchover point. Note that this will usually happen for every simulation that you run. You'll increase your value until you get to the pressure peak, and then it'll drop off. So this is pretty normal with the exception of this little spike in the middle. So let's investigate this spike a little bit more closely. The dotted line that you see over on the right side of your graph is going to be the point that you're at in your animation. So we can see that we're at 98%. So we're almost to the end of our filling. All right. So what I'm going to do is I'm going to take my animation back to just before that pressure spike. And we want to evaluate what's actually going on in our fill at that moment. And the reason I'm going right before the spike is because right at the spike is usually after the phenomenon occurs. And usually what happens to create these, in this case, it's just a little spike. In some cases, it'll actually be a pretty big spike, especially if it's closer to the end of fill. Usually those spikes will be larger and a little bit more sensitive. So at this point in our fill, we can actually see over here on the top right corner of the part, we can see that there's actually an end of fill region being filled out at that point. So even this small end of fill, there you can see that there's nowhere for the melt to go after it reaches this point. Once this end of fill is reached, you can almost think of it like the melt hitting a wall, which I mean it is. So what you can think of is that melt is hitting a wall, and now it has to bounce back and go in either this direction or this direction. We call this a momentum shift of the flow of the plastic. If that momentum shift actually happens through the gate, and that's where we get these little spikes, or in an extreme scenario, if maybe this end of fill over here occurs before the end of fill down at the bottom right corner of our part, then we actually get a giant spike right before the switchover, which can definitely increase your maximum pressure value, increasing the amount of pressure required to fill this part, which might push this into a higher tonnage machine. So we want to avoid that if at all possible, and that's really the primary reason why flow balance is so important. All right, so moving on to the third question. This is going to be all about weld lines. So where are the weld lines on our part? how can we identify the weld lines, and more importantly, how can we evaluate the quality of the weld lines? Because a weld line happening is not necessarily a huge problem unless it's going to cause our part to be weaker than the part normally would be. And I'll say in most cases, the weld line will decrease the mechanical strength of the part between 60 and 90%. So there's never really anything good that comes out of forming a weld line. But if we can optimize the strength of that weld line, then maybe that strength reduction is not going to be as much of a factor. All right, so before I show weld lines, there's actually two classifications that we have for two melt fronts meeting. You can see this diagram over here. We're flowing around a particular feature, whether this be a hole or a boss or anything that would cause the melt front to diverge and reconverge after that feature. If the connection angle between the two melt fronts is less than 145 degrees, less than 145 degrees, we call that a weld line. So a weld line is going to be more crucial than what we call a meld line, which would happen if the angle is greater than 145 degrees. So you can see that with a meld line, this angle is much more shallow. With a weld line, the angle is much more acute. All right, so let's see what that actually looks like. In the results, the first thing we're going to do is identify where the weld lines actually are. So I'm going to click on the weld line result in our filling stage. It's going to be the third from the top. And on our part here, we'll be able to see all of the weld lines. One thing to note with the weld line display, it will show up as red lines on the mesh pattern. So if I were to overlay my mesh again, we would see that these lines follow the mesh lines. That's just how the result works. We're looking to change that in the near future. But it gives you a general idea of where crucial weld lines occur. So these red lines will only represent what I just mentioned as weld lines. The meld line classification does not show up in the results. So anything greater than 145 degree, what we call the meeting angle, anything greater than 145 degrees meeting angle is not going to show up. All right, so if I go into my weld line meeting angle result, we'll see that the scale is from 0 to 145 degrees, and we'll now see that our weld lines have a color contour on them. All right, and that's all fantastic, but what does this actually mean? When two melt fronts come together, you can almost think of it like if you were to put two balls of Play-Doh together. If you were to just kind of put them side by side, it's very easy to pull them apart. And the same thing follows with plastic. I mean, Play-Doh is a plastic of sorts, right? So if you have two melt fronts that are coming together head on, it's going to be actually very easy to separate those melt fronts because there's not any interaction between those melt fronts. They just kind of go up against one another, and maybe there's a small amount of interaction in order for them to actually bond slightly. But it's going to be very easy to separate or crack your part at that region because the weld line meeting angle is so low. The more acute the weld line meeting angle, or the lower your weld line meeting angle, the weaker your weld line is going to be. So if we can, ultimately, if we can make this weld line into a meld line, getting it over 145 degrees, that would be the ideal scenario. Unfortunately, in most scenarios, that's not going to be possible. We can see in this case that at this moment right here, we get the lowest weld line meeting angle, which is pretty expected. And we can actually visualize why this is the lowest weld line meeting angle. If we go to our melt front time result, you'll see that the weld line will go away, but we can go to display. So instead of the result tab, we'll go over to the display tab. Then we'll go over to the molding defect section, and we'll turn on both the air traps and the weld lines. We'll need the air traps in just a moment, so you might as well show those as well. And then what I can do, if I go back to my result tab, I can take my animation back to when that weld line is formed, and we can see that the melt fronts right here are pretty much just colliding with one another. causing that really low weld line angle. After that, however, you can actually see this angle here. Maybe it's like 90 degrees, something like that. It actually opens up pretty quickly, which is a good thing. But right at this feature, if I were to apply any sort of external force, I would be really worried that my part would fail there because it has such a low weld line meeting angle. The other qualification that we use is what we call weld line temperature. So weld line temperature will just allow us to see the average temperature of the melt fronts as the weld line was created. If the weld line is pretty close to the melt temperature, then that is pretty ideal. The hotter the weld line, the more interaction is possible because the more vibration is occurring, the easier those polymers are able to interact with one another on the different melt fronts. And if that's the case, then the melt fronts, they just kind of penetrate one another and they're able to merge together and form a stronger bond. So the hotter the weld line, the stronger. If we have a cold weld line, a weld line that's very far below the melt temperature, then we definitely have a cause for concern there as well. So when it comes to weld lines, we're really looking down towards the bottom of our scale. We're looking for a really low temperature weld line or a really low meeting angle weld line. All right, moving ahead here. The fourth question, will there be any air traps in our part? Air traps can come in two varieties. We have internal air traps and we have perimeter air traps. So this graph here represents an internal air trap. They're pretty uncommon for the most part. They usually happen because of a drastic thickness variation. In this diagram here, the outside perimeter of the part is pretty thick, and the inside rectangle here is quite a bit thinner than the outside. So what happens is the melt will prefer to flow in the easiest to flow region or the highest cross-sectional area region, which is going to be around the outside, and then it'll try to fill in the inside once it's done filling the outside using the amount of pressure that it can. But what happens is it's very difficult to get any sort of air removal method, maybe like an ejector pin. Vented ejector pins are actually becoming more and more common these days, but most of the time it's really difficult to predict the exact location where that air trap is going to occur, which is where simulation can come in handy. But at the same time, you usually want to eliminate this as a possibility. The other type of air trap is much more common, and it's perimeter air trap. So perimeter air trap will just be kind of around the outside of the part or around the end of fill regions or maybe the corners of our part and so on. So if we look at the part that we have in our pre-run simulation here, you can see that most of the blue dots are just kind of on the outside in some like corners, or maybe like these bosses are at the bottom of the boss. So whenever the melt velocity goes to 0 in a localized region, that's where these little blue dots will show up. So it's not always necessary that these blue dots, we need to place a vent at every one of these blue dots, but usually these blue dots can really give you an idea as to where you might want to start placing your vents in your mold design. Now in the simulation, we don't necessarily have to place venting. You might have heard of the term venting before. We don't have to place a venting condition in order for these blue dots to show up. These blue dots will again show up whenever the velocity of the melt goes to 0. So these will show up even with a normal injection molding analysis without any sort of venting applied. All right, one other thing to note is I kind of alluded to it earlier. Not all of these blue dots are necessarily places that you would want to vent, so you will have to use your own discretion, your own judgment to figure out which blue dots are actually the crucial ones. For example, if I go into my melt front time, again, these blue dots are kind of overlaid so I don't lose them when I go over to the melt front time. And that was done again through our display tab. All right, and if I take my animation back to when that air trap was theoretically created, we can see that in this case, the melt front is kind of almost just laying over top of this feature. So this feature might not need to be vented. The air might not even be trapped here. So you just have to kind of use your own discretion and use your own judgment, result interpretation capabilities to figure out if these air traps are actually necessary to be vented. All right, the fifth question here is how large is the maximum stress level? The amount of stress on your part, or the stress distribution on your part, is going to be actually very important to the final warpage that you're going to see in the part geometry. And the result that I usually like to look at is the shear stress result. And from kind of a macroscopic standpoint, you can almost think of the shear stress result as the ripples in a river. If you've ever watched the flow down a river and you see like a rock in the middle of the stream, you'll actually see that there's a ripple of the water around that rock. And that's because the flow is actually interrupted because of that rock. So usually whenever you have the plastic flow will be the same, and the stress is really the interruption of the flow along the flow length here. So you'll see that in any sort of interruption, so you can see around this feature, you'll actually get a pretty large amount of stress. Over here, we get a pretty large amount of stress. And actually up here, when we have this kind of elevation change, if you will, you can see that there's a little bit of a stress after that feature as well. So usually, whenever you have an interruption to your flow, that's where your shear stress is going to increase. Now, one thing I'll note about the shear stress is that the value isn't all that necessary to correlate. I know a lot of material suppliers and other softwares out there will give a recommendation for the maximum shear stress. But the thing about shear stress is there's no possible way to measure the shear stress directly. There's no physical measurement device that can measure shear stress. Therefore, shear stress is really just a simulation value that we can compare to another simulation. So if I were to run another simulation at a lower flow rate, maybe I see a lower shear stress. If I run a higher melt temperature, maybe I see a lower shear stress because the material is able to move a little bit easier. So you can use this as a comparative value, but the absolute value here is really difficult to correlate because a lot of the values that we get from the material suppliers are actually, or the recommendations that we get from the material suppliers are usually based on simulation. So it's usually, for that reason, it's usually a simulation-driven simulation requirement. So it's not really a useful value. It's more of a recommendation based on previous simulations that they've run. So that's something to keep in mind with this. But you can really get an idea of where the flow is interrupted the most by looking at where your highest shear stress regions are. Another way to look at this is actually through the isosurface. Most of the time, the highest shear stress is going to occur right at the surface of your geometry, but there are instances where there's a high amount of stress in the middle of your geometry, and you're not going to be able to see that from the outside. So using the isosurface result, we're actually able to break down the result here and only look at a particular value. If I go up towards the maximum value of our shear, we can really start to see where the highest shear regions are. So you can see around this feature and kind of on the backside of that elevation change. That's usually, it looks like those are the two highest shear regions. You can see that the values will kind of go all the way out until you see that the maximum really isn't 2 MPa. You can see that most of the elements in my part are pretty much gone at 1.658, and that's another reason why I don't recommend to look at the magnitude of this result, because the magnitude can be a little bit misleading sometimes as well. All right, so we've reached the halfway point. If you do have any questions, you can shoot those over to the chat, but we're going to keep plugging away here, and we're going to go through the last 4 questions. All right, the next one is going to be, is the clamping force too large? So clamping force is actually a derivative of the sprue pressure. So the amount of pressure that we apply over a distributed area is going to give us our clamping force. And the clamping force is going to be a value that you can correlate directly to the amount of tonnage that a machine or that a clamping system can output. So this can really give you a good idea as to whether your part is sufficient for a machine, or whether maybe you need to increase the machine capacity. Maybe the machine is too big for the part. Maybe you can save a little bit of production cost by going to a smaller machine. These are things that you can evaluate through the simulation. So I'm going to go to XY curve, and then I'm going to go to clamping force. So clamping force, just like the sprue pressure, the clamping force is also an XY curve because they are derived from one another. And you'll actually see the contour of your clamping force is going to be pretty much the same as your sprue pressure, with the exception of maybe this beginning portion where we go through the gate, because the gate really doesn't apply any sort of clamping force on the part directly. So we can see these little spikes here. You see that it goes all the way to the maximum value here and then maybe drops off at the end, just like our sprue pressure. So theoretically, what I would want to do is go all the way up to the maximum value here, which in this case is 137. You can even left click there to show where that maximum value is. And this is what most people will do. And I'll tell you right now that this is the wrong method. We're looking right now at the clamping force in the filling stage. Now, as we force more material into our geometry, as we pack out our part, that force is actually going to increase until the material starts to shrink. For that reason, the clamping force result in the filling stage is not going to give you the full story of what's actually happening across the cycle. So rather than looking at the clamping force in the filling stage, I'm actually going to go into my packing results. And I'm going to go into the XY curve of my packing results, and we'll go to clamping force there. You see that my little tag still shows up, which was the maximum during my filling stage. You can see that right after the filling stage, you can see that force actually increases again because we're actually packing out the geometry. And we get to this maximum value, which might be something like 165. You can see that that's maybe like a 10 to 20% increase in the pressure, or in the clamping force, which is crazy. We always want to make sure, this is probably one of the most important points in the filling stage that you need to remember. We always want to look at the clamping force during the packing stage, because more times than not, the clamping force will be higher in the packing stage than it is in the filling stage. Now we can actually see that this the curve kind of gets to a maximum value and then gradually starts to decrease. And the reason for that is there's really two competing factors at play here. The pressure that we're applying is obviously going to increase the amount of clamping force, but as the material shrinks, it actually decreases the amount of force that we're applying to the clamping system. And once the shrinkage of the material overtakes the amount of packing that we're applying, then we start to see this decrease. And this will apply for almost every part geometry that you see. As that material starts to shrink down, as it cools, it will shrink. And as the material shrinks, it will, the clamping force will gradually decrease. And eventually your clamping force should get all the way to 0 as your material shrinks off of the mold. And that is something that we can simulate, as you can see here. So most important thing here is to just make sure that you're looking at the clamping force in the packing stage, and then we can really accurately designate which machine, or what size machine we should be putting this part onto. Moving ahead here, the 7th question, is there any hesitation or race tracking issues? Hesitation and race tracking are actually due to the same phenomenon. Hesitation is going to be kind of the prevention of flow in a particular area, and the leading or race tracking is actually the opposite. It's actually the kind of the propulsion of material in a particular region of the part. These are both thickness-based phenomenon. So whenever I have a thickness change in my part, usually that's either going to cause hesitation. If I go from a higher thickness to a lower thickness, usually the material will try to not go in the thinner region because plastic is lazy. It will not want to go into the thinner regions the part. It'll try to fill out the thicker region first, and then once it's done with the thicker region, it will go into the thinner region. We actually saw that earlier with the air trap result. That was also a hesitation phenomenon. Leading, on the other hand, the material will again prefer to flow in the thicker region. So you can see in this part here, the top region is much thicker than the bottom region. These features on the bottom of the part are actually quite thin. Therefore, the material prefers to flow across the top, and it creates this sort of leading phenomenon. All right, so these two are kind of interrelated, and to get an idea of whether this result is whether this result is actually taking effect, or whether this phenomenon is taking effect in our part, we really need to get an idea of the thickness variation throughout our geometry. So what I'm going to do is go to model thickness. So I'm going to go to result and then model thickness, not to be confused with the thickness, XY plot thickness. We're going to go to measurement model thickness. All right, and this will actually tell us what the different thicknesses are on our part geometry. So there's a couple of ways that I can evaluate the thickness. I'll show you one way that works all the time and one way that works most of the time. All right, so the first and probably the best way to evaluate this is to use the scale modification. So if I go to the top of my scale and then left click, drag it downwards, we'll actually see that color distribution change. And once a major surface on my geometry turns red, then I can evaluate this. I can just take the maximum value on my scale, and that will be the thickness of that feature. So in this case, this feature over here is 3 millimeters. If I continue going downwards until maybe the nominal thickness turns red, we can see this is around maybe 2.5 millimeters. And if I keep going, maybe I can see the thickness of this feature here, which this one here is about 2 millimeters. So these are things that I need to be paying attention to, and this is something that I might be able to get a premonition for if I look at the thickness before I go and run the simulation. I should be able to figure out what I would be expecting in my results if I already knew the thickness distribution. The other way to evaluate this, and this is actually a really awesome tool that we've included into Moldex3D 2020, I'm going to restore my scale. I'm just going to left click drag this and bring it all the way back up to the top. I'm going to use what's called a probe. You can either use the probe down at the bottom right corner of your screen. This one's a little bit more accessible, especially if you're not in the result tab. So you can use the probe function down here at the bottom right corner of your screen next to the snaps, or you can go up into your result ribbon and use the probe function. And then you can simply just probe at different regions on your part. Maybe I'll take these 3. All right, and these probes obviously don't really tell us a whole lot, but they will if I go over to the display tab and turn on my probe values. And you can see here that my thick region is 3 millimeters, my thin region is 2 millimeters, and my nominal region is about 2.5 millimeters. So this is another way that you can evaluate the thickness. I mentioned earlier, this will work most of the time, but in scenarios like this over here, sometimes the mesh pattern and the way that we measure the thickness isn't always 100% correct. Sometimes you'll get some abnormalities like this. So you just want to pay attention to that. If there is an abnormality, usually you don't want to take a thickness probe there. You might want to just use the scale reduction like we did earlier. All right, so now that I know what my thickness distribution looks like, now I can go back to my filling results. And the primary result that I'm going to use for hesitation is going to be the melt front time. So melt front time is going to tell me whether I have, and this is going to be in the filling stage. If you're still in the packing stage from the clamping force result, then we'll go back into the filling stage, melt front time. And you can actually hide these probes. If you want to go over to your model tree, you can hide these probes. They aren't going to help us anymore. I'm also going to turn off my air traps and weld lines while I'm in the display tab here, because they're just going to get in the way. All right, so what I can do is I can play my animation, and most of the time I'll actually be able to see if there's any sort of hesitation or leading. It'll actually be very, very obvious most of the time. In this case, because we have a very subtle thickness change or a very subtle thickness variation, there isn't a whole lot of obvious hesitation or leading. You can see that through this region. This was our thin region. This is what I would pay attention to the most. You can see that there's not really a whole lot of hesitation that's obvious. But I would expect there to be some sort of delay in the melt front through this region because it has a lower cross-sectional area than the rest of my part. So for this reason, we actually have another result type that we use for this, which is called the pressure result. If the material it has a hard time moving through a particular feature, then it will experience a higher pressure drop or a higher pressure change through that feature. We can evaluate pressure change really easily by using what's called the isocontour display. You can think of the isocontour display kind of like an elevation map. If you were to look at an elevation map and you see contour lines very close to one another, then you would know that the elevation is changing very quickly there. So it would be like a cliff or a mountain, the side of a mountain or something like that. The same thing occurs here. If these contours are very close to one another, that means that the pressure is changing very rapidly or more rapidly than the other regions. Usually I change the number of contours here to a higher value. Maybe in this case, I'll go to 100 to see if we can see maybe a phenomenon. So what I'm looking for is to see if the contour lines are closer to one another in a particular region versus another region. And we can actually see kind of that the spacing between these contours here is a little bit thinner than the spacing between these contours here, which tells me that, as I would expect, the pressure drop through the thin region is a little bit faster than the pressure drop, or a little bit higher than the pressure drop through the nominal region. We can actually see if we compare the nominal region to the thick region. Remember, this little wall down here was 3 millimeters, whereas the nominal was 2.5. We can actually see that the contours are pretty far apart from one another with respect to the nominal region. So this result really allows you to evaluate where your material is flowing very easily, which is where the contours would be spread apart, or where there is a restriction in the flow, which would be where those contours get very close to one another. In this case, I would say that it's not a very impactful hesitation, but it's always something that you want to be paying attention to, especially when you have a thickness variation in your geometry. All right, the 8th question here, how significant is the viscous heating effect? So viscous heating is probably one of my favorite topics just because there's a lot that goes into the shear distribution. If you joined one of our standard trainings, you probably already know about this result because this is one of the ones that actually do go through in the standard training. This is the filling temperature. So the temperature distribution throughout our geometry is going to give us an idea as to which phenomenon is dominating our flow temperature. Now, I say which phenomenon is dominating our flow temperature. There's actually 2 factors at play here. There is the cooling of the melt front. So as our melt front gets further and further away from our gate, the melt front would theoretically cool down because the gate is where we're actually heating the material. However, as the material flows through the part geometry, the moving material is going to rub up against the stationary material, which is closer to the mold surface. And that friction that's occurred there can actually start to increase the temperature of the melt front. So we need to figure out which of those forces is dominant in our flow. If we have a shear dominated flow, then we would expect that the temperature will increase from our melt entrance to the end of fill, meaning that our end of fill will be a higher temperature than our gate. And cooling dominated fill, we would actually see that the temperature would just be hottest at our gate. So that's what we're going to evaluate here. And looking at the surface, you can't really say too much. You can see that the temperature at the end over here is a little bit hotter, but that will almost always happen on the surface specifically. But this actually isn't an indication of what's happening through the center of our part. We're actually more interested in what's happening in the core of our part rather than what's happening at the skin. So what I'm going to do here is I'm going to look at the isosurface result. The ISO service display again breaks down our result to one single value, and I can see where the highest value of this result lies if I take my slider all the way over to the right, maybe not all the way over, but very close to the right. And we can very obviously see in this case that our highest temperature of fill is at the end of fill rather than at the gate, which means that in this case we have a shear dominated flow. A shear dominated flow is something that you don't want to see. You almost always want to see a cooling dominated flow. If you want one of the factors to dominate, it's usually the cooling that you want to dominate, and we'll see that in just a moment when we get into the packing results. But shear dominated flow just basically means that the temperature is highest over here towards the end of fill, leaving the gate a little bit cooler. We can actually see how much higher temperature we have over here. If we look at our melt temperature, you can either go back to your process to get your melt temperature, or a little shortcut for you. If you go over to your information tree, so in the same toolbar as your project tree and your model tree, you can get to your information tree. It's just a circle with an I. And then at the bottom here, we can see what our input melt temperature was. In this case, it was 250 degrees Celsius. So our ISO service here is at 262, and we actually go all the way up to 273. So there's a possibility that we are almost 20 degrees above our melt temperature over at the end of fill here. If I even go a little bit further, you can see that this side isn't as extreme as this side, but you can see that as we get closer to 270, that's 20 degrees above our melt temperature. So just the flow alone through our part geometry is increasing our temperature by 20 degrees, which is pretty crazy. Usually you want to see your melt temperature stay between plus or minus 10 degrees of the melt temperature. In an ideal world, in this scenario, we see that we have a shear dominated flow. In an ideal world, you would actually want to balance the shear domination versus the cooling domination. If you can balance those out completely, then your melt will be at an even temperature throughout your part geometry. That means that the part is going to shrink more uniformly, which is ultimately going to lead to a lower amount of warpage. We'll get into why that is in the cooling stage, but optimizing this sort of effect is going to benefit you in the end, because you're going to get a lower variance in shrinkage, because a difference in temperature is going to lead to a difference in shrinkage, and a difference in shrinkage is going to lead to warpage ultimately. So if we can balance the temperature throughout our geometry, then that means that our part is going to shrink more uniformly and give us less warpage. All right, the ninth and final question here is there an overpacking issue? We use this question more to just evaluate the packing effects in general. So there's actually a lot of results that we're going to look at here. I'm going to go down into the packing stage. And the first thing I'm going to look at is the packing pressure. And I'm going to get my ISO surface. The ISO surface isn't going to help me out too much here. In an ideal world, the packing effect across our part should be relatively uniform. We would want to distribute the amount of pressure that we're applying to the melt entrance throughout the entire part geometry. The pressure application that we're using through the melt entrance can only be distributed to molten material. Once the material freezes off, we're not able to distribute that pressure any further. So, for example, if our gate is frozen, or if the material around our gate is separated from the rest of our geometry, then our pressure will be very distributed right around the gate region, kind of like what we see here. If our material is still molten at the end of the packing stage, then you'll actually see that this contour will be more distributed throughout the geometry, and you won't have the zero value that you see here through the majority of our part. All right, so now our job is to figure out why our pressure is so concentrated around the gate in this case. So what I'm going to go to is a result called the molten core. Like I mentioned, the pressure application can only be distributed through molten material. The molten core allows us to see directly how much of the material in our part is actually molten. All right, so we see that right around our gate, we have a bunch of molten material. The blue material that you see here is above the freeze temperature or is molten. We can actually see that the material at the end of fill, which shouldn't be a surprise because of the temperature distribution we just saw in the filling stage, the temperature at the end of fill is still molten as well. So it looks like in this case, there's actually almost like an island around the gate here, which is likely why we're seeing such a concentrated pressure distribution right around the gate region. We're not actually able to see. We're not actually able to distribute this pressure any further because the material is separated. The molten material around the gate is separated from the molten material at the end of fill. And this is the primary reason why we hate shear dominated flow. As we get into our packing stage, there is molten material that's always going to be coming through our gate. That's just always going to happen because the melt temperature is always 250. So we're always pushing that 250-degree material through our part, which means that it's going to solidify pretty much last. The material at our end of fill became 20 degrees hotter than the original melt temperature. So as we get into our packing stage, this material over here is actually going to be hotter than the material coming out of the gate. So this material is going to solidify at either an even rate to the material coming out of the gate or maybe even a slower rate than material coming out of the gate. However, the material between those two regions is kind of stuck in limbo because it's at the coolest temperature in our geometry. So the material at the middle of our flow, the material between the gate and the end of fill region, is going to solidify, separating the gate from the rest of our part geometry. And it causes this sort of pressure concentration. And this sort of pressure concentration that we're seeing is actually a really huge problem, especially if I apply this pressure for a long amount of time, because I can actually shove so much material into my part geometry that when my mold opens, the material actually expands. And this is not only dangerous, but it causes the part to deform very obviously. So the dimensions of the part actually increase, whereas normally you would expect they would decrease based on the shrinkage of the material. So this pressure application, we definitely want to identify it, and we want to fix this if at all possible. Usually this sort of phenomenon specifically that we're seeing in this part geometry can be fixed by just either slowing down our fill, reducing the amount of shear that happens. Maybe I can even increase my melt temperature to make the melt temperature a little bit more uniform throughout my part geometry. So this all kind of stems from the filling stage. And you can kind of create a DOE for yourself if you wanted to fix this. Now, the amount of pressure concentration that we have on our gate is ultimately going to impact the amount of shrinkage that we're seeing in our part. And we're going to get into an effect called PVT in the cooling stage. And then PVT is going to explain a lot about why the volumetric shrinkage distribution is so important. But we can actually look in the filling and packing results, more importantly, the packing results. We can actually see what our distribution looks like before we allow the cooling to take effect. So what I can do here, you can see the result is pretty much completely at the bottom of my scale or in the blue color. So I can just take my scale down and see how that shrinkage is distributed throughout my geometry. And we can see that around my gate, the shrinkage is really low. And at the end of fills, our shrinkage is pretty high. The reason being is because the material at our gate is very well packed out, even though it's at a higher temperature, whereas the material at our end of fill is not very well packed out and it's at a high temperature. So the shrinkage there's no way to reduce the shrinkage based on the packing. It's all just going to shrink down as it normally would. All right, and that pretty much wraps it up for the filling and packing results. There's a couple of results that I didn't go over. If you want to evaluate any results that I didn't go over specifically, you can simply just double click on those results and it'll give you a description of what that result means and possibly what that result can be used to evaluate throughout your part geometry.
Thank you for watching the Moldex3D Advanced Tips and Tricks. Please don't forget to leave a like on the video if you enjoyed the content. If you'd like to suggest a future topic, feel free to let us know down in the comments. And finally, if you want to see more content like this in the future, don't forget to subscribe to our YouTube channel.